Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Andy Nightingale of Arteris. We're going to talk today about scaling performance in AI. When we get into AI, there's a lot of data that needs to be processed and it needs to be processed quickly. What sort of challenges are engineers running into with this?
As data processing is absolutely key to AI design, AI chip design. There's actually a bunch of other factors that are posing real challenges to designers right now. So one of these is the time to market pressure. So as AI innovation it rapidly evolves, as we know, there is increased pressure on chip designers to deliver new designs faster. So achieving this without compromising on performance or reliability adds complexity to the entire development process.
So how do you manage some of this complexity? It's just becoming an enormous amount of data that needs to be moved around a chip. You've got a lot of compute elements. Designing these chips is becoming a nightmare.
Oh, absolutely. I mean, if we actually look across the key verticals that we serve, and these are automotive, communications, consumer electronics, enterprise computing, industrial, AI applications is actually a horizontal that cuts across all of these different verticals. So looking at the key points, we've got the performance versus the power trade-offs. So we've got AI workloads that require high computational performance whilst also demanding energy efficiency. So balancing the need for faster processing with power limitations, that's critical, especially for these edge devices. We've got scalability challenge. So AI models, particularly deep learning models, are growing in size and complexity. So designing AI chips that can scale performance to meet the increasing demand while maintaining efficiency is a significant challenge. We've got latency sensitivity. So AI applications such as real-time inference for autonomous vehicles and robotics, these require minimal latency, ensuring low latency performance across various use cases while managing the complexity of AI workloads is a key design hurdle. And there's a couple more I can think of off the top of my head. Memory bandwidth, data bottlenecks. So AI workloads are very memory intensive. Chips must handle large amounts of data with really high bandwidth. So overcoming data transfer bottlenecks between processing elements and memory is critical to avoid performance degradation. And then the final one is the need for heterogeneous integration into SoCs for AI chips. So these AI chip designs often need to integrate various types of processors, the XPUs, if you like. So we've got CPUs, NPUs, GPUs, TPUs, all within the same system. And this introduces challenges in interconnect architecture, into power management, and communication efficiency.
So let's dig into this.
Sure.
There's really no single AI, right? It's now AI for different use cases. It's AI for different workloads. It's AI for different vertical markets.
Absolutely. If you look across all these different verticals, we've got the edge computing inference applications, we've got edge computing training, we've got embedded computing inference, and then we get into enterprise. So this is where you get the tensor units doing enterprise level training, and then edge computing for industrial, again with inference applications. And all of these verticals have their own specific requirements. So, for example, in Edge, we've got a focus on modularity, hierarchical design. Let's pick embedded. They really want to focus on area and power efficiency. And then in enterprise, for example, the focus on scalability and hierarchical design and easier routing and layout. So every, as you say, every vertical has its own challenges. Even though we say AI is a horizontal, there are specific, AI challenges for each of these.
But there are some common things you can do here, right, in order to make it easier to design these chips.
Yeah, let me show you. So here's the way we see it. So in this space, we've got heterogeneous computing. in terms of solutions that are needed. So this is integrating CPUs, GPUs, and NPUs to optimize performance across these different AI tasks that we've just seen. We've got a solution requiring AI accelerators. So these, for example, enterprise specialized GPUs or tensor processing units and NPUs in consumer to optimize AI workloads. We've got dynamic power scaling solutions. So we've got DFS, dynamic frequency scaling, and DVFS, dynamic voltage and frequency scaling to reduce power consumption by adjusting power and frequency based on the workload. We've got chiplet architectures. So we've got chiplets that integrate multiple dies, improving the performance and design flexibility. We've also got advanced memory hierarchies as solutions here in the AI space. So high bandwidth memories, HBM, and 3D memory stacking address memory bandwidth and latency bottlenecks. We've got software optimization tools. So AI compilers and frameworks optimize software for specific hardware and speeding up development. We've got modular IP blocks. This is pre-verified IP blocks that allow reuse, reducing design time and verification efforts. We've got AI model compression, so techniques like quantization, reducing model complexity for better hardware performance. And last but not least, there's this new network on chip or NOC technology that really allows different architectures, interconnectivity architectures, to give scalable, efficient communication between these different processing elements, and in combination with tooling IP, help designers build AI NOCs faster or AI solutions faster using the NOC technology.
What is tiling here? Is this chiplets or is it something different?
So one specific solution is the focus point for this talk, and it's network on chip tiling, which incidentally is separate from physical chiplets that we just mentioned. Network on chip tiling is more of a soft tiling approach. And one fundamental NOC architecture used in concert with NOC tiling is that of using mesh interconnect, which is heavily featured in today's AI use cases.
And this is classic mesh networking, right? Where you're doing peer-to-peer, able to move data in any direction you need to move it.
Yeah, exactly right. So looking specifically at the automotive segment, there's a use case here that focuses on AI application for machine vision with object detection. So multiple AI accelerators, including image pre-processing modules, feature extractors, neural network accelerators, are employed in the vision pipeline. So as mentioned, NOC mesh topology provides a most effective communication infrastructure for these processing elements, allowing seamless data exchange and collaboration among the accelerators. To your point, the processing elements, really need to access data from any particular direction.
You're moving a lot of data in these mesh networks, and you're moving it in a lot of different directions. So you really have to keep track of what's going on here. What sort of challenges do engineers run into in terms of developing these?
In order to achieve the above use case that we just saw, an NPU design without this NOC tiling technology that we're introducing here as a solution, each network interface unit or NIU and transport element is unique and must be implemented separately to connect the processing elements together. So this actually increases complexity and the time it takes to configure. So this, of course, impacts the time to market, as balancing this NOC complexity with verification and implementation efforts becomes very much more difficult. So in this case, designers commonly choose to break the design into smaller units and then manually connect them together to build up to the final design. So this approach has worked very well in the past, but does incur additional latency, because what you're doing is you're connecting these different networks that you've created together, and as you bridge across them, you're actually introducing a latency penalty.
That has a big effect in terms of both performance and power, right?
Absolutely. And we need to actually remove these bottlenecks if we're going to scale our system effectively.
Beyond mesh networks, we also have to think about keeping all this data coherent, right?
Yeah, absolutely. So for completeness, we're showing here also a coherent NOC with a mesh configuration too. And NOC tiling in this context is mainly the ability to find the socket for a CPU cluster and being able to replicate that as a NOC tile into other sockets on the mesh.
Engineers have been working with at least a knock in the past and sometimes multiple knocks. How does this change things?
So if we basically look at the tooling requirements for putting NOCs together as they become more complex and they become more and more manual efforts to define each individual processing element. So that the challenge here is really to bring in tooling that takes that risk out of repeating multiple processing elements that essentially exactly the same IP. The only difference is the connection points that actually make up that mesh connection. So really, what we really want is automated tooling that makes the ability to replicate large numbers of processing elements and their individual connections very rapidly, and automate that as much as we can. And this is where we bring in the NOC tiling in the tooling. So on the right-hand side of the image here, we see that the tooling visualization of actually configuring those different tiles. And that actually maps onto the design intent, if you like, on the left of building up this NPU for our vision processing application.
Does it matter if this is multiple chiplets in a 3D package or if it's a planar SoC, or is it all the same?
It's all the same. What we allow is basically not composition. So the different network on chips that connect all these different processing elements come together as one whole SoC. So you focus in on the NOC topology for the particular task that you're interested in, and then you actually stitch those together. You compose those, into the larger SoC design.
And when you think about machine vision, it's not just machine vision. I mean, could be robotics, it could be autonomous vehicles as well, right?
Absolutely. Anything that requires some level of either object recognition or any image processing task that needs, really snappy response times, this will apply to.
By snappy response times, this could be two cars going at 60 miles an hour in opposite directions, and you need to react that fast.
Absolutely. You need very quick reaction time for obviously vehicles, but similarly as well. And if somebody steps out from the pavement in front of a vehicle, it just needs to react as quickly as physically possible.
So we measure almost everything by PPA, power performance area cost. What sort of improvements do you get out of this approach?
Yeah. So the advantage of the NOC tiling solution for the designer, and of course their final design, include simplified design complexity. So the modular nature of NOC tiling simplifies the overall design process, allowing for easier handling of complex systems, reducing interconnect challenges and improving the routing efficiency. It leads to reduced latency. So this NOC tiling optimizes data flow between processing elements, minimizing communication delays and improving overall performance for latency sensitive applications. We've got flexibility and reusability. So the tile-based approach provides flexibility in design customization, while reusing verified tiles ensures design reliability, reduces risk. And then, of course, the adaptability for various workloads. So NOC tiling can be adapted for different AI workloads in terms of AI designs. If, for example, the NPU that we saw for TPUs, for GPUs, providing versatility across a range of applications. So there are three additional benefits that I think are worth illustrating, with an example. So first is scalability aspect. So this is being able to scale up the performance. The second one is in power reduction, and the third one is improved time to market. So if we actually zoom in on the power efficiency side of things, NOC tiling supports dynamic power management, allowing unused tiles to be turned off, reducing power consumption and enhancing energy efficiency in AI designs. Not tiling even allows for easy participation in SOC power reduction features, as all of the power management connectivity is replaced or replicated, sorry, within each tile. So in the example we have here, back to the NPU design, this is benefiting from dynamic frequency scaling, and in this case is able to save around 20% on average energy consumption in this case. Yep.
And a lot of these technologies have been out there for quite a while. And you think about mesh networks, that goes all the way back to early 2000s. We've been talking about peer-to-peer. We've been talking about advanced packaging for a while as well. Why now? What's coming together? What's different about the tiling, and why do we need it now versus in the past?
Yeah, that's a great question, Ed. So why we need it now really is we've actually reached this tipping point with design complexity. So previously, mesh networks were, reasonably manageable, in terms of size. Now they're actually going up to, from a typical 4x4 or a 5x5 mesh, which is still quite large, they can be 8x8 or even larger. Now, if you have to configure each individual element inside that, all its connection points, its service network, its data path, its observability, an 8x8 mesh, you've got 64 different processing elements you have to configure and connect up. That's a heck of a lot of work. So what we're doing here is we're really enabling a tile to be defined once and then replicated in a modular fashion. And actually, so instead of doing that 64 times, you're actually doing it once and telling the tool, I'm going to reuse this multiple times. You go and configure the difference in connectivity, what the ID of the tile is, how it connects into the network. You handle that side of it. And then the designer is really then freed up to work out how to resolve other issues like the memory and latency challenges versus just the basic, scale up of these huge designs.
This also provides you some resiliency in the design too, right? If something goes wrong in one tile, you can now route around it.
Yeah, I mean this is a great feature, but again, in the tile, you've got different memory modes. You could actually then, on the fly, if you actually detect that there's a failure in a particular tile, you can reroute around it and actually assign another tile with that ID and actually continue doing your processing. This is a great solution for example, dark silicon in some cases where you actually you can do a check to power up, check where the good tiles are, much like we did in the old days with hard drive sectors, and actually configure the memory map accordingly.
Andy Nightingale, thanks for a great explanation.
You're welcome, Ed. Thank you.